Hi everyone, so we're going to look today at the last part of the moments chapter, so the last bit of chapter 4, and we're going to start with this today. So we're looking at moments questions when the line of action of the force is not perpendicular to the point about which we're taking moments. And if you think about the questions we've been doing so far, if ever we've had a rod or a plank or whatever, if it was sitting on some support, then the reaction was perpendicular. If it was being held up by a rope, then the tension was perpendicular. And if someone was sitting on a seesaw or something like that, then again the weight was acting downwards, as is the weight of the rod. So they're all being perpendicular to whichever point on that rod we're taking moments about. But what if the rod or the plank of wood, whatever it might be, is being, let's say, held up by strings that aren't perpendicular, and then the tension is acting at an angle to the horizontal and an angle to the perpendicular, to the vertical there. So that's what we're going to look at today. Now, before we start doing that, we just need to think about what's called resolving forces. And we've thought a little bit about this before when we've been looking at forces as vectors with i's and j's or column vectors. But any force can be thought of as a vector because it's got size and it's in a particular direction. So it's got magnitude, but it's also got direction. So let's just say if we had a force, let's call it F, acting at an angle of theta degrees. Now what up to the horizontal? Now what I can do, I can replace that force with its components horizontally here and vertically here, where the overall action of this, and we have seen this before in class, but the overall action of these two forces, the red and the green together, would result in this. And it is going back to vector questions that you've all definitely seen before. You know, if I go along the red and then I add the green, I am definitely going to end up with this vector. So I'm allowed to do this. I'm allowed to, from the point of action of this vector, force F, point of action of this force, I'm allowed to split it into these two equivalent forces acting perpendicular to each other. Okay? And if we think about this right angle triangle here, then this, cos theta, adjacent over hypotenuse, so this is going to be the hypotenuse times cos theta, so that there, the red, is going to be F cos theta. Okay, and the green, which is going to be equivalent to this vector here, not sure if you can see that, so equivalent to that vector there, the green, this vector, is going to be F sine theta, because sine is opposite over hypotenuse, so this one is going to be F sine theta. And that will always be the case, you know, the component that's adjacent to the angle, because cos in SOHCAHTOA is adjacent over hypotenuse, the component that's adjacent to the angle is always going to be the one that's cos theta, and the other component, the one that's not adjacent to the angle, is always going to be sine theta in there. And Miss Webster, sometimes when she's teaching this, she talks about this component being cosy with the angle. So that's where you can remember the cos comes from. I like to think about it as being adjacent. So adjacent over hypotenuse, so it's adjacent. That's why the cos theta is in there. Okay, anyway, that's just a bit of an introduction to the idea of splitting a force into its perpendicular and perpendicular, vertical and horizontal components, and that's what we're going to do these questions on moments today. Okay, so let's have a look at our first example. And so our first example here, we've got a non-uniform rod, mass 3 kilograms, so non-uniform, really important that. So non-uniform, meaning the weight is not going to be acting in the centre. It's got mass 3 kilograms, length 5 metres, so you can see our diagram here. It's resting horizontally in equilibrium, and it's supported by 2 strings, so we've got tension in these strings. This one's at angle 40 at end A, and this one's at angle 55 to the horizontal at end B. Okay? And it's asking us to find the magnitude of the tensions in the 2 strings. So this string X and this string Y, what are the tensions in those 2 strings? So I'm going to add some tensions onto my diagram, and I'm going to add the weight onto this as well. So here I'm just going to call this T1. And this one, I'm going to say that's T2. Okay, and they're definitely not the same because they're different strings. The only other thing that's happening here then is the weight. It's non-uniform, so I mustn't put it on in the centre. And it doesn't really matter where I put it on because the distance will work itself out at the end. So if I put it on the wrong place here, it doesn't particularly matter. My answer will still work out okay. So I'm just going to put my weight on here. Let's call that C. And my weight here is 3G. Okay, and this total length is 5 metres. Okay, so let's see what the question wants us to find. It wants us to find these two tensions, so the magnitude of the tensions in the two strings, and it also wants us to find the distance of the centre of mass from A. So I'm going to call that distance X, and then this distance will be 5 minus X, if I use that later. Okay. Just seen the number in there is not quite right, so let's change that to A and B. So part A, find the magnitude of this. So we need to look at some force equations. We've got moments we can use, but don't forget as well, we can always use up and down here. Our up minus our down must be equal to 0 because there's no resultant motion, no resultant force vertically in this. And equally now as well, horizontally, the whole thing's in equilibrium. It's just resting there. So horizontally, there must be no resultant force either. So I'm going to do that first because that's just going to get the tensions involved without having to worry about these distances. And then for the distance, I'm going to do some moments to get that involved. And sometimes in questions, you might have to do a mixture of up, down, left, right, moments to get enough equations to find the unknowns that you need. Okay, so let's have a look. I'm going to, first of all, let's resolve vertically. So I'm going to tell the examiner I'm taking up as positive. So in the up direction, what I need to do now is to split these tensions, these forces, into their perpendicular components. So here, if I split T1 up, this one's the one that's adjacent, so this is going to be T1 cos theta. And this bit here is T1 sine theta. And then on the other side here, this component is going to be T2 cos theta, and this component is going to be T2 sine theta. Hope you can see that. You might have to zoom in. So let's have a look at resolving vertically. What's happening vertically? This component of T1, this component of T2, and then in the opposite direction, the 3G weight acting downwards. So that means T1 sine theta. Sorry, that should be 40. Let me actually put them in because I know what those angles are, don't I? So that's 40 degrees and that's 40 degrees. And on this one, that's 55 degrees. And that's 55 degrees there as well. So here, our theta, we know what that is in these questions. This is 40, so sine 40. This is 55, so sine 55. Cos 55 in that direction, cos 55 there. Okay, let me get back to this. I'm going to start that again. So T1 sine 40 degrees upwards, plus this one's acting upwards as well, T2 sine 55 degrees, and then minus my 3G acting downwards. There's no other forces going on. So vertically, that's what's happening. And there's my equation 1, okay? And I've got two unknowns in this. G isn't an unknown, don't forget, 9.8, we can put that in. So T1 and T2 are mine unknowns. So now let's resolve horizontally to get another equation with T1 and T2 in, and then I can solve some simultaneous equations. And again, tell the examiner, I'm going to take right as positive. So let's have a look. We've got T2 cos 55 positive. We've got T1 cos 40 negative. And again, my resultant force in all of this is equal to 0 because the whole thing's in equilibrium. So that's going to be 0 as well. And there's my equation 2. So I've got two equations, two unknowns. They're not particularly nice equations, but that's okay. So I'm going to get, let's say maybe T2 as the subject here, sub it in here, and then I can use my calculator to find the value of T1. So from here, T2 is going to be equal to T1 cos 40 over cos 55. And then I'm going to substitute that into equation 1. So I'm going to substitute that in here. So that's going to give me T1 sine 40 degrees plus T1 cos 40 degrees over cos 55 degrees times my sine 55 there, minus 3g is equal to 0. So sorting this out, T1 out as a common factor because I want to find out what T1 is, sine 40 plus, I could change this, sine over cos is tan. Don't know if you've done that in pure, I think you probably have, but anyway I'm just going to leave it because I'm going to type it into my calculator. So cos 40 times sine 55 over cos 55, that's going to be equal to my 3g, 3 times 9.8. So let's sort all this out. 3 times 9.8 divided by all of this. Move this up slightly so you can still see that, hopefully. So I'm going to work out T1. Let's just grab our calculators. Oops. And do that. So 3 times my 9.8. 3 times my 9.8. And then I'm going to be dividing that by all of this here. So sine 40 plus cos 40 over cos 55 and that's times by sine 55. So I didn't think it would like that. I think I'm missing some brackets, so let's put them in. Okay, what am I doing wrong? 3 times that over sine 40 plus cos 40 over cos 55 times sine 55. What's a big bracket there? Found it? Okay. So 16.92756, etc. Sorry about that, messing about with my calculator, but it was telling me I had a bracket here and didn't have a bracket at the end. But obviously you can work these bits out individually and then put them back into your calculator as well. 16.927, so 16.9 newtons to 3SF. Okay. I'm going to move my paper up. I'm going to substitute this back in. Not this value though, my full value from here. So I think I'm going to store that as A. So there's my answer in as A. I'm going to use that to find out what T2 is by substituting back in to this here. So let's just move this up so we can see. Okay, so T2 is going to be equal to this thing, T1, which I'm going to substitute in from there, times cos 40 over cos 55. So that's going to be this answer times cos 40. It's not going to like that bracket again. Okay, there we go. Divided by cos 55. Close the bracket. And that's going to give me T2 is 22.6077. So T2 is 22.6 newtons to 3SF. Okay, so that's the first part. Let's move that down. That's the first part of the question done. Find the magnitudes of the two tensions. Quite a lot of work in that, so probably worth quite a few marks, maybe 5 marks or something like that in the new exam. So we've got our T1 and our T2, and now part B is asking us to find the distance of the centre of the mass from A. So I'm going to have to use moments here to get this distance involved. So let's have a look at doing that. Let me get another piece of paper. Okay. So let's have a look. Let's try and get rid of one of these forces, so we don't need to worry about it. So I'm going to take moments about A. We could take moments wherever you like. I'm going to take it about A because then I don't need to worry about this force here. I'm just concerned with this and this. So let's do that. Let's take moments about A. And you will get the same answer if you take moments anywhere else. So take moments about A. Tell the examiner I'm taking clockwise as positive. So 3G is going to tend to make this thing turn clockwise. So that's going to be positive times my X. And then this T1 sine 40 now is acting at A. So that's got no turning motion around A. This force here is acting at A, so that hasn't either. Over here, let's have a look at T2. So this component of T2, actually the line of action of that force is going right through A. So the distance of that one from A, the perpendicular distance of the line of action of that bit of the force is 0. But this force, this one acting this way, so that one was acting through A, this one acting upwards is definitely perpendicular and it's this full distance away. And this is tending to pull us anti-clockwise. So that's going to be minus T1 sine 55 degrees. There's no other forces acting, so this bit's pulling us anti-clockwise, this with clockwise. Nothing here is having a turning effect, so that's going to be equal to 0. And T1 I've got from my answer here. Okay, so T1 from my answer here, my 16.927. Okay, so let's just have a look at that. We're going to put that in here. I'm going to do a bit of working out. I'm going to take this across. I'm going to take my 3G down and I'm going to get my X value. So I'm just going to do a little bit of sorting out on my calculator. So T1, which I already had stored, 16.927 times, sorry, I'm not sure if you can see that, times sine 55. And then I'm going to divide that by 3G, 3 times 9.8. Okay, and that's given me my answer for X. My X value here is going to be, I can see I've made another mistake, not going very well this evening. Another mistake here, look, that should have been T2. So there we go. Let's try that again, Mrs. Pauling. So let's go back to our answers. Have I got that answer stored? So there's my answer now, 22, don't know if you can see that, 22.600077 times that by my sine 55. And then divide that by my 3 times my 9.8. Doesn't feel right to me. I'm just having another look at this. You're probably shouting at the screen. 3G times X. I haven't put my distance in here, have I? Goodness sake. Okay, let's try that again. So 3G times my perpendicular X, distance X, minus my T2 sine 55. And that's going to be multiplied by this perpendicular distance, 5. Moments is force times perpendicular distance. Okay, let's try that again. Let's just recall my A value. So there's my T2. Let's times that by sine 55. Let's times that by 5 now. Let's divide that by 3 times 9.8. Okay, that feels like a better answer, so we should get there. X is equal to 3.149, etc. So X is equal to 3.15 metres to 3SF. Okay. I'm hoping you were shouting at the screen there where I was making mistakes and missing things off. But there we get our answer overall. And we're going to do another couple of these questions as well.